Chapter 6 is about eigenvalues and eigenvectors. And we introduce eigenvalues in section 6.1. And ax equal to b could be thought as a linear equation for a steady state. In general, the steady state is reached after some transient response. So when you, for example, when you throw a battery, and usually there is some response inside the battery, something like this, and it's fade out and there is no problem. But sometimes there's a transient, and then maybe a big fire happen. This kind of divergence. So anyway, in many systems, and you have a transient, when something happen, when you throw a battery, or it's just any kind of impulsive attack to a system, and you get a transient response, and then you reach a steady state response. So when you study about system, usually there are two states, and transient response and steady state response. But ax equal to b is about linear equation because there is no time axis. But we want to know how about change? How about change or dynamics? Or transient behavior. We want to know not only a steady state, but also a transient response. So we want to solve this differential equation. Differential equation. This is the differential equation, and this is difference equation. And this is a continuous time system. A continuous time system. Yeah, this differential equation is a description of continuous time system, and this is a discrete time system. So we're dealing with a discrete time system. Anyway, we want to solve that, but we cannot solve this kind of equations. Cannot be solved by Gaussian elimination. So if we want to solve that kind of differential equation or difference equation, we want to know dynamics, then we need to solve this equation, ax equal to lambda x, and here x vector is called eigenvector of matrix A, and lambda called, this is a constant, lambda is it's a scalar, it's called eigenvalue. Corresponding to eigenvector x. And eigenvector is not could not be a zero vector. If zero vector is allowed, you can see that the equation is always true because zero vector equal to zero vector. For example, we're solving this difference equation, and if uk is an eigenvector, then we can write auk will be lambda uk. So we can write this equation as uk plus 1 is equal to lambda uk, which is just a geometric sequence. And the matrix A is gone, and it's a very simple thing. And we have to understand the meaning of this equation. For this equation, there is no direction change for eigenvector. I mean, ax equal to lambda x means that there is no direction change after the system. I mean, so we consider a multiplication is just a system, and input signal is x vector, and output signal is ax. And in this equation, what we have is lambda x. That means, scalar multiplication means that there is no direction change. I mean, for example, well, in daily life, when we talk about this vector and this vector, we say this is opposite direction vector, we say. But in mathematics, because this is origin, and the two vectors are in the same line, in that case, we say the direction change, there is no direction change. So that's why I say lambda x means that there is no direction change. For example, think about rotation of globe, which is Earth model. We have a globe, I mean, and the Earth, there's a rotation axis. This is north pole, and this is south pole. This is Earth rotation. And in this case, we could say A is just a rotation operator. And if we think about, if you think A is just the rotation of a globe, what is the eigenvector for the rotation? Well, the answer is this axis. The rotation axis vector, any vector, rotation axis vector, will be eigenvector of the rotation, because after rotation, this is after rotation vector, a vector after rotation, and that vector does not change. So in this rotation, lambda is equal to 1 because there is no change, and x is just the any vector on the rotation axis. For example, if we think about the vector here, maybe what country, whatever, and this vector, if you rotate the globe, and it'll change the direction. So that vector is not an eigenvector. The eigenvector is for the rotation, eigenvector is just a vector on a rotation axis. That's the meaning of eigenvector. As an example, we consider this matrix A, and then we calculate A square, and then we calculate A cube, which is 0.65, 0.525, 0.35, 0.475, and keep continuing, we get 0.6, 0.4, 0.6, 0.4 after a to the 10, a to the 100. But if we need any of this calculation, a to the 100, well, it's too complex. So to calculate this vector, and we can use eigenvector and eigenvalue. So I mean, a to the 100 was found by using eigenvector 1 and 1 over 2, not by multiplying 100 times. Why do we need that? I mean, a to the 100? Because sometimes we model, for example, this is state for the moment k plus 1 is equal to a times the state. This is a state vector at time k, and this is a state vector or a system state vector at time k plus 1. And well, you know that uk will be a to the 100. I mean, well, I think we said k, so I think it should be k and u0. So this is, we can say this is a state vector at time 0. We might say this is initial vector or initial condition. So sometimes we want to know after a long evolution what will going to happen. We want to know that. So in that case, we want to calculate a to the 100 or a to the 1000, and we want to know whether it will converge or diverge, and we want to know that. And in that case, to calculate that thing, we don't multiply 100 times or 1,000 times. We use eigenvalue to calculate that. So I think this understanding is important. So we think a multiplication of a matrix is a kind of operator or system, and then input is x vector, and the output will be ax. But But now we are thinking about eigenvector and eigenvalue. So we will call x vector is eigenvector of A. And so we think that what is x vector is a direction invariant vector of A. I mean A multiplication. So there's a system, and eigenvector is a invariant vector. So after, because it'll be lambda x. So but lambda is a scalar. Lambda is eigenvalue, but it's a scalar. So it means that we are looking for eigenvector and eigenvalue, and then we are looking for eigenvector. That means we are looking for invariant thing for matrix multiplication. And as I said before, invariant is important in mathematics because it's something essential. Because if it's not essential, it'll change. But eigenvector, after multiplication, it does not change its direction. And so we want to know what is eigenvector because it's essential one. If eigenvalue is equal to 0, in that case, ax vector is 0 times x vector, which is 0 vector. And then x vector is in null space. So now I know that if the eigenvalue is 0 and a null space, any vector, any non-zero vector in null space will be eigenvector for the eigenvalue 0. And another special case is if A is equal to identity matrix, and then the eigen equation will be Ix will be lambda x, and in that case x will be lambda x, and so lambda is equal to 1 and x is any vector, any non-zero vector, because eigenvector should not be a 0 vector. So any vector, I mean in this case, if A is equal to identity matrix and eigenvalue is equal to 1, and any vector will be eigenvector. Okay, let's see an example. And we want to solve this equation, Ax equal to lambda x, and want to find x vector, which is an eigenvector, and also we want to find the lambda, which is eigenvalue. And we want to solve that equation, and then first we change equation like this, which is lambda I times x vector. I is the identity matrix, and then so we change the equation in this way, and we write, but we know that eigenvector, we want to find eigenvector, but eigenvector is not 0 vector. So if A minus lambda I, for example, if A minus lambda I inverse exists, then x vector will be 0 vector. And so we fail. So to find eigenvector, the necessary condition is that determinant of A minus lambda I should be 0. I mean, A minus lambda I should be a singular matrix. So we call this equation is a characteristic equation. And we solve that. This is 0.8 in this example, minus lambda, 0.7 minus lambda, 0.3, 0.2. And this is 0.8 minus lambda, 0.7 minus lambda, minus 0.06. After some calculation, we get lambda minus 1, lambda minus 1/2. So eigenvalues will be 1 and 1/2. So now we know that A minus I and A minus 1/2 I will be singular. Because the eigenvalues are the roots of characteristic equation, but a characteristic equation is determinant of A minus lambda I is equal to 0. And then I want to find eigenvector. First, we consider that case lambda is equal to 1, and we calculate A minus I, and then we get minus 0.2, 0.2, 0.3, minus 0.3. And we want to solve. I think we have to write again to explain. Now we solve this one. X vector will be 0 vector, because the equation is like this: ax is equal to lambda x, but now we have A minus lambda I x vector will be 0 for if x vector is an eigenvector. So now we solve this equation, and we can see that x vector is 0.6, 0.4. But any multiple of this vector will be okay. I mean, for example, if you times 100 will be okay, but we're gonna stick to it, because we know that any multiple except 0, I mean any non-zero multiple of eigenvector will be an eigenvector. And now we consider the case 1/2, and in this case we calculate 1/2 I, and this is 0.3, 0.3, 0.2, 0.2. And we want to find the solution of this equation, because the answer will be eigenvector for the eigenvalue 1/2, and the answer is 1 minus 1. And as I said before, any non-zero multiple of this vector will be eigenvector. And now we know that for I think we should write this is x1 and this is x2, and we will call it lambda 1 is 1 and lambda 2 is 1/2. So we have 2 eigenvector, and then we have 2 eigenvalue. So this one, for the lambda 1 and this one for lambda 2. And we know that ax1 vector will be x1 vector because lambda 1 is equal to 1. And then we know that we multiply both sides a, and then we get a square x1 will be ax1, and ax1 is equal to x1. So in this way, we know that a to the n x1 vector will be x1 vector. That means after a long evolution, x1 vector component doesn't change. If input vector has some component of x1 vector, and then that component, after multiplying a matrix, it does not change. It will stay. But if you see that ax2 will be 1/2 x2 by the definition of eigen equation, and we know that, and then we multiply a matrix on both sides, and we get a square x2 vector will be 1/2 ax2 vector, and it'll be 1/2 square x2 vector. So in this way, we can see that a to the n x2 vector will be 1/2 to the n x2 vector. So now we can see that if the input vector has the component of x2 direction, it will fade out because we have 1/2 here. So for example, after a long evolution, for example 100 times, so we multiply 1/2 to the 100, and so it'll fade out. So if the input vector, we just decompose the vector to, so there will be x1 component, and that will be some x2 component. But the x2 component, after some evolution, it will fade out. But we know that the x1 component will stay forever. So in general, in this eigen equation, we have, you think about a square, and we multiply both sides a square, and we get lambda ax, and it'll be lambda square x. So in this way, we can see that a to the n x vector will be lambda n x vector. So for example, we want to know, an eigenvector of a to the n is also an eigenvector of a. Eigenvector does not change for a to the n, but eigenvalue change. Eigenvalue change to lambda to the n, but eigenvector doesn't change. You consider a, and after that you consider a to the n, but eigenvector will stay the same. Now we go back to the example, and the first column of a matrix could be represented as a linear combination of eigenvector, because we know that eigenvector x1 has eigenvalue 1, and eigenvector 2 has eigenvector 1/2 x2. So we know that. And we can represent the first column of matrix A as a linear combination of two eigenvectors. And A times the first column will be A times x1 vector plus 0.2 x2 vector, and it'll be lambda x1, lambda 1 x1, and plus 0.2 lambda 2 x2. So it's easy calculation. Lambda 1 is equal to 1, so this is 0.6, 0.4, and this is 0.2 and 1/2, and x2 is the second eigenvector, which is 1 minus 1, and it'll be 0.7, 0.3. And so the first column of A to the 100 will be A to the 99 times 0.8, 0.2, which is the first column of A, is equal to A 99 to the 99 and 0.6, 0.4 plus 0.2 and 1 minus 1. And this is x1, and this is x2, the second eigenvector. So it'll be lambda 1, 99, x1, and plus 0.2 lambda 2 is 1/2, 99, and 1 minus 1. So it'll be almost equal to 0.6 and 0.4. I'm showing you that why the first column is changed to 0.6 and 0.4 as much time have passed, and we get a 0.6. We see that the first column converges to x1. The reason is this. The second column of A was 0 times 3, 0.7, and it was 0.6, 0.4, minus 0.3, 1 minus 1. And so we can say the second column is just first eigenvector minus 0.3, second eigenvector. And similarly, we can see that A 99, 0.3, 0.7, that'll be lambda 1, 99. Lambda 1 is equal to 1, and lambda 2 is equal to 1/2, and 0.6, 0.4, minus 0.3, lambda 2, 99, 1 minus 1. And we know that it'll be almost 0. And lambda 1 is equal to 1, we see. And so that's why it'll be 0.6, 0.4. Now we can see that all the columns, first column and second column, will converge to the first eigenvector. And we can say that x1, the first eigenvector, with lambda 1 is equal to 1 is a kind of steady state because it doesn't change. And x2 component with lambda 2 is equal to 1/2 is decaying mode. So as n goes to infinity, columns of A to the n approaches steady state. And A is called a Markov matrix because A is 0.8, 0.2, and 0.3, 0.7. We can say the sum of first column is 1, and the sum of a second, all the entries of second column is equal to 1. And so in that case, this matrix A is called a Markov matrix. Now we will consider projection matrix P. And for projection matrix, column space projects to itself. So a Px will be X if X is equal to a column space of P. I mean, for example, if we draw a plane, and this is column space of P, and if the vector stays in the column space of P, even with projection, it will stay the same. So, yeah, it's already in there. So already there, and projection does not change anything. So that's why we have this one. But the null space of P projects to 0. So P x will be 0 vector if this is by definition x vector is n of P. Well, this is rather obvious. In this case, this is origin, and we have some kind of line here. In this example, the line here, and vector here on this line, after projection, it goes to 0 vector. So any vector like this vector, also this vector, after projection, it goes to 0 vector. So projection matrix, I mean, we have two eigenvalues. One is just 1 for the vectors already in a projection space, and the other vector is orthogonal to the subspace. And if you think about a subspace projection, the vector in the subspace will be eigenvector, but eigenvector has eigenvalue is equal to 1. But in orthogonal, this example, the line here, the vector will be an eigenvector, but in this case, eigenvalue is equal to 0. So we write here, in this case, lambda is equal to 1, and for this case, lambda is equal to 0. So this is an example of projection matrix, and we can see that this is rank 1 matrix, and we can think this is just Q transpose. So just outer product of that vector, and so this is if you draw it, and there's a line here, and if we have that vector and we consider the projection into this line, so maybe we can say this is y is equal to x, and we consider the projection to here, and so this vector will be p vector after projection. But anyway, now we consider this matrix to get a characteristic equation, and 0.5 minus lambda, 0.5, 0.5, 0.5 minus lambda, and we get this one, characteristic polynomial, and it'll be lambda minus 0.5 square minus 0.5 square, and it'll be lambda minus 1. As I said before, we have two eigenvalues. One is 0 and the other eigenvalue is equal to 1. And we see that lambda is equal to 1 case, and p minus I will be minus 0.5, 0.5, 0.5, and minus 0.5. And we can see that eigenvector will be 1, 1, because when we multiply this vector with this eigenvector, when you multiply that, and we're going to have 0 vector. So that's why x1 is 1, 1, and this is eigenvector. And for lambda is equal to 0, and we consider just p, and p is 0.5 all over, and we can see that x2 could be 1 minus 1. And I said many times, any non-zero multiple of eigenvector will be eigenvector. And so we have two eigenvector, and we see that when we draw the diagram, and we see that, so this one is eigenvector direction, which is x2, and x1 direction, obviously x1 direction here, x1 direction here, so 1, 1, 1, 1 is we have this direction. This direction is x1 vector. Yeah, obviously, because after projection, x1 stays the same, so that's why we say lambda is equal to 1. That means after multiplying p, after projection, it does not change. That means lambda is equal to 1. The meaning of lambda is equal to 1, and after transformation or after operator, after applying operator, that component stay the same. That means that is the meaning of lambda is equal to 1. And lambda is equal to 0, that means it's gone. After the operation, after multiplying P matrix, it's gone. Because you see the x2 component is here. After the projection into the line, into this line, y is equal to x, and there's nothing because we get a 0 vector. And that is the meaning of lambda is equal to 0. If the matrix is symmetric, then its eigenvectors are orthogonal. So we can make it orthonormal, because we can just normalize. It's still it'll be still eigenvectors, so we can make it orthonormal. So this is important fact, because in quantum mechanics or quantum computers, when you learn that, and operator is just a symmetric matrix, and a lot of times we assume that we just say that eigenvectors are orthonormal, but I think you need to know this fact first. And also another fact is, in general, eigenvalues of A is equal to eigenvalues of A transpose. And another fact is, for Markov matrix A, each column adds to 1. And so obviously each row of A transpose adds to 1. And so we can write A transpose is just A1 transpose and AN transpose. And so we consider the eigenequation. So A1 transpose AN transpose and x1 xn is lambda x1 xn. And so we want to find the eigenvector and eigenvalue for A transpose, but we can see that this equation is correct. I mean, we can write all one vector and all one vector here, because when you do a dot product of this row vector and all one vector, what you're going to do is just adding all the entries of A1 column. But we are considering a Markov matrix, and each column adds to 1. So it'll be 1 here, because all the entries of first column of A will be 1. Similarly, and we can have this equation. So now we prove that, because A transpose, the eigenvalue of A transpose is the 1. Lambda is equal to 1. I mean lambda is equal to 1 is an eigenvalue of A transpose when A is Markov matrix. But we already know that eigenvalues of A is equal to eigenvalue of A transpose. So lambda is equal to 1 is always an eigenvalue for Markov matrix. And another fact is projection matrix is a singular matrix. I mean, so a determinant of P will be 0, and so that means determinant of P minus 0I will be 0. So lambda is equal to 0 is an eigenvalue. We explain what is the eigenvector for this. Lambda is 0 eigenvalue. I mean, when we consider the projection to the subspace S, and this is the origin, and the vector here, vector in this direction, will be the eigenvector for the projection, because after the projection it goes to origin. I mean 0 vector. And so, and another fact we need to know is projection matrix is P transpose is symmetric. projection matrix is symmetric matrix, and we know that projection matrix is A transpose, A inverse A transpose, and we calculate, we can easily see that this is true, and we know that we have orthogonal eigenvectors for projection matrix eigenvectors. I mean, in general, even if we don't have projection matrix, if as long as the matrix is symmetric, and we're gonna have orthogonal eigenvectors and even also normal eigenvectors. In this example, we have two eigenvector, and one is 1, 1, and the other one is 1, minus 1. They're orthogonal, but I mean, in general, if we have symmetric matrix, and their eigenvectors will be orthogonal. This is really important fact. So we know that eigenvector for lambda is equal to 0 will be in null space of A, and eigenvector for lambda is equal to 1 will be a column space of A. So projection keeps the column space and destroys the null space. So in this example, we consider the projection onto the line y is equal to x. If we have a v vector, if we have equal to 3, 1, and we can decompose to 1 minus 1 plus 2, 2, but we can see that is 1 minus 1, that is 1 minus 1 is this direction. So what is it? This is so this vector is related with lambda is equal to 0, and this vector is this direction 2, 2. So it's on the line, so it's related to lambda is equal to 1. So after projection, we consider a PV. So this vector is after projection. What we have is 0, 0, and 2, 2. So we have 2, 2 after projection of V vector. The reason is that the 0, 0 means that because it's from the, lambda is equal to 0 vector component, so it's gone. That's why it's gone. And but this direction is preserved because this one is just lambda is equal to 1 component. That direction. So that's why it stayed the same. So we have 2, 2 after projection of 3, 1. Now we see another example, which is exchange matrix 0, 1, 1, 0, and then we can find eigenvalue using determinant, just calculating this one, and we can find that lambda is equal to plus minus 1, and for lambda is equal to 1, we can see that this one 1, 1 is x1, the first eigenvector, and then lambda is equal to minus 1, and we have 0, 1, 1, 0, and 1 minus 1 is equal to minus 1, 1. And so this will be x2. And so we have two eigenvectors and two eigenvalue here. And we can see that if we multiply the matrix E over and over again, and what will happen? We like to consider this E to the 100 and X vector, but in general the X vector has two components. One is X1 component and the other is X2 component. And then after decompose the X vector, and then we can expect that X1 component will stay the same. And how about X2 component? And it'll oscillate because lambda is -1, and that means it never fade out. It will oscillate. We solve this characteristic equation. This is called characteristic equation. To find eigenvalue. And this polynomial is called characteristic polynomial. A characteristic polynomial. And because we consider just square matrix, well, maybe I didn't mention that, but anyway, when we talk about eigenvalue and eigenvector, we always talks about a square matrix. So A should be a square matrix. So the size of matrix should be n by n. And so the degree of this characteristic polynomial will be n. So degree of determinant of a minus lambda I will be n. And so we're gonna have n roots for characteristic equation. We have n roots, but n roots. We have n roots for this characteristic equation, but it could be repeated. So for this repeated case, sometimes we don't have enough eigenvector. We don't have n eigenvector. Let's see an example. Example 4. A is equal to 1, 2, 2, 4. And we want to have eigenvalue. We want to find eigenvalue and eigenvector. And we know that a determinant of A is 1 times 4 minus 2 times 2. It will be 0. So this is singular matrix. And lambda is equal to 0 will, lambda is the 0 eigenvalue will exist. But anyway, we find a minus lambda I, which is 1 minus lambda, 4 minus lambda, 2, 2. And determinant of a minus lambda I, which is characteristic polynomial, will be lambda square minus 5 lambda. And so we have two eigenvalue, which is lambda is equal to 0 and lambda is equal to 5. And A is 1, 2, 2, 4. So 1, 2, 2, 4. So the eigenvector will be, x1 vector, eigenvector will be 2 minus 1. You can verify that. You multiply A and you get a 0 vector. And A minus 5I will be minus 4, 2, 2 minus 1. And x2 will be 1, 2. So we have 2 eigenvalue and 2 eigenvectors. We'll talk about determinant and trace. And for example, we consider 1, 3, 2, 6 matrix, and after elimination we get upper triangular matrix, which is 1, 3, 0, 0. And eigenvalue for the matrix A is equal to 0 and 7, and eigenvalue for U is equal to 0 and 1. So we can see that elimination does not preserve eigenvalues. But we need to know that determinant of A will be the product of eigenvalue, and the trace of A, which is the sum of diagonal entry, and will be the sum of eigenvalue. For 2 by 2 matrix case, for example, if trace is equal to 3 and the determinant is equal to 2, then we can immediately can see that lambda is equal to 1 and 2. I mean, in this case, we have a lot of candidates for a matrix. For example, 1, 9, 0, 2, or 3, 1, minus 2, 0, and 7, minus 3, 10, minus 4. All the matrix, they have this eigenvalue. So given eigenvalues, we have many possibility. We can make many matrices. Now we consider the case of imaginary eigenvalues. This matrix Q is a 90-degree rotation matrix, and we see that because we are in a 2-dimension, a plane, and we rotate the vector in 90 degree. So in this a 2-dimension, a 90-degree rotation case, actually we don't have any real eigenvector, because if you see this equation, and lambda should be a kind of this is eigenvalue, but it's the meaning of that is just the stretching factor. But rotation is not allowed in this equation. Just stretching or squeezing vector will be eigenvector. So this is if we do a 90-degree rotation and there is no real eigenvector. But we could have imaginary eigenvector here. So we calculate this one will be minus lambda minus 1 minus lambda minus 1 here. Is the determinant of Q minus lambda I, which is lambda square plus 1. So lambda will be plus minus I. And so lambda 1 is I, and lambda 2 is minus I, and lambda 1 plus lambda 2 is equal to trace, which is 0, and we can verify that lambda 1, lambda 2 will be determinant which is equal to 1. But there is no a real eigenvector. Because the definition is that the eigenvector should be stretched or squeezed, but at this time always a vector will be rotated 90 degrees, so you cannot find any real vector. But you can find eigenvector if we allow a complex number, a complex vector. So we can see that I1 will be eigenvector for I, and also we can find 1I is the eigenvector for minus I. So we can find two eigenvector, which is x1, we can call it, and this one will be x2 for eigenvalue minus I. For orthogonal matrix, the property is Q transpose is Q inverse, and the lambda, the absolute value of lambda is equal to 1. If Q is skew symmetric, well, this is Q is equal to minus Q transpose. In this case, lambda is pure imaginary. And if S is symmetric, we can say lambda is real. And well, it's about eigenvalue. They're all about eigenvalue. For eigenvector, symmetric and skew symmetric and orthogonal matrix, for these three cases, and eigenvector are orthogonal. We need to define the dot product for complex vectors, but anyway, I think it's very important, the property. So if we have any special matrix like orthogonal matrix, a skew symmetric, or symmetric matrix, eigenvectors are orthogonal, so we can make it orthonormal. This is the end of the lecture for section 6.1.